We're going to jump straight into an introduction from Thomas on epidemics. So Thomas moved into mathematical epidemiology postdoctorally with Matt Keeling at Warwick before winning a personal fellowship, then moving to Manchester, where he is now a professor at mathematical sciences. He co-leads the group in mathematical epidemiology with Ian Hall and Lorenzo Pelez, and is currently head of probability and statistics. His current research includes inference of household data, network models, and including the public and patients in mathematical epidemiological research. Thank you, Thomas.
Hello, thanks very much for the nice introduction I wrote 5 minutes ago about myself. I mean, you know, my imposter syndrome is a bit off the scale with Valerie in the audience talking about the history of epidemic modelling and how it works. But so what am I doing today? I'm going to try and present some key results from epidemic models. And the emphasis is going to be on techniques for analysis and the insights that the models provide. So I'll show some simulations and results. I won't show the proofs, but if people want to ask me, I can say how you derive things or provide the detail. There are really hundreds and hundreds of relevant references here. If I were writing a scholarly document, I would include all of those, but to give a proper account of how we got to them, it would need a lot of referenciness and really break up the flow. So lots of this is sort of very classic, or I could say, oh, this was derived by, you know, 100 years ago and then improved by this. But there's a long story behind all of this, how we got here. But the idea is I'm just presenting pedagogically. So, and having seen the other intros, I think this is more mathematical, but I think that does honestly reflect the fields, which is mainly people with quite technical training who've got interested in epidemiology. Although there's a very important large minority of modelers, just sociologically, who were biologists or medics or so on and have learned to model, and that's a very, very important part of the scientific community. But I think the field is dominated by people with a technical background, right? And so the one joke, okay, I may make up the jokes, but the one. Everyone's got the picture of Kate Winslet writing on the board, right, R0, and this is another one I found, and this woman is someone from the far future's consciousness that's been uploaded into the present day to try to stop a super intelligent computer from killing everyone. And she's dealing with a pandemic in the present day, but as a kind of future person whose consciousness is in the present. So it's a bit less grittily realistic than the movie Contagion, but she is writing the R0 equations on the board correctly. So it's an option. It's an alternative to the classic Kate Winslet screen grab where she writes a load of R0 values to explain why everyone should care about this stuff. Okay. So starting point is going to be the Markovian SIR model. So we have a vector X, bold and large because it's random, and bold because it's a vector, and that contains 3 integers. So it's a process that's indexed by time, t, which is real, and then each of these is an integer counting the number of people who are susceptible, infected, and recovered. They're going to be constrained in this case, so that the sum of those integers is always n, right? The rules are going to constrain it. So for all positive and 0 times, and this integer n is called the population size. So I think this is a good starting point for lots of reasons. You could be more general, you could be more specific. Lots of people start with the differential equations, but I think the random models are very important, right? And actually existed alongside the differential equation models. And really, when you look at real epidemic data, it's always terribly noisy. So it seems very odd that in a way, it seems odd to start with the deterministic case. So there are just two events associated with this chain, and they have state-dependent rates of happening. So just quick sense check: who knows who knows what a Markov chain is and has done some modelling with a Markov chain? Okay, so sorry to the energy people. Right, so Markov means it doesn't have a memory. And so the basic point is, intuitively, a rate is just, you take a small step forward in time, you multiply the length of that time step by the rate, that gives you a very small probability that the event happened. So rate's like a limit of a very small step in probability, right? So it's like you say, oh, lightning, you know, Ebola epidemics appear at about a rate of 1 per year, right? There's a zoonotic transmission about every between 1/2 and 2 years, right? So that's a rate of happening, or lightning strikes at a rate, right? And what that means is in a small period of time, there's a small probability, and the rate is that probability divided by the time, right? And so you have rates and events. So infection happens at a rate given by this rate constant beta times the number of susceptibles and the number of infectives. The idea is the susceptibles and infectives are all mixing homogeneously. When they bump into each other, the infective can infect the susceptible, right? So that's why it's a product form. I'll talk about relaxing that assumption later. We divide by n here, here because these have been defined as integers, right? So this divide by n, you could just absorb it into the beta, but if you divide by n, then the beta tends to take sensible numbers to put into a computer, like 0.5, 1, 2, 3, like for realistic systems. So the beta will tend to be something, yeah, whereas if you're modeling like hundreds of thousands of people, your beta might end up being very, very, very small, right? If you don't divide by the m. So it's just convenience, right? But there's nothing special about this. But so sometimes people look at putting a power on this n actually, but that's another story. So that's infection, and what infection does is it depletes the susceptible population by 1 and increments the infectious population by 1. And then there's recovery, which is that each infectious individual recovers at a rate, gamma, and that increases the number of removed individuals. Yeah, so it's a random model, and direct simulation, that means you sum up the rates and pick from an exponential with that rate for the next event, and then you pick the probability of which event happened proportional to the rate that it's part of, right? So there's a nice bit of maths. Incorrectly attributed to Gillespie. I was told it was one of Kendall Senior actually wrote this down as an algorithm, but people tend to call it Gillespie's algorithm. But direct simulation is another thing that avoids having to name it. And so what you get is trajectories that look like this. So here I pick quite a small, if people would like the code, by the way, I've got, this is all in Python. I can give people the code or make, I'm hoping to build this into a bit of a resource. So maybe I'll make a site at some point if people ask. So, but this is quite small. So we expect randomness to be quite important for 100 people, right? So this might be like an outbreak in a school or small hospital, that sort of thing, right? A bit of a hospital, care home, right? These are sizes of population we do deal with. So we're going to start with 99 people susceptible and just 1 person infected. And like I said, beta is 2, gamma is 1 in this case. So the susceptible population in this model can only go down. So it does go down each time, but there's a lot of variability in that, just caused by the innate randomness of the model. And each of the infectious trajectories goes up and down. It can wiggle up and down. And that is what real epidemics look like, right? So sometimes if I really want to hammer the point, because particularly during COVID, we got an awful lot of, oh, this is just theory, you know, it's just these people running off. And sometimes what I do is show just dozens and dozens of like actual epidemic curves going up and down, right, for different countries, different diseases. It's like, you know, this isn't a completely fanciful idea, right? That epidemics go up and down, and it's because of these mechanisms. So since here we've constrained these integers to sum to n, I don't really need to show the recovereds as well, right? Or the removed, so sometimes we'll call them removed. Yeah, so that kind of follows. But if you think about it, that can only increase. So those curves tend to look like these S curves, but flipped. So they tend to start at 0 and go up. So we always end with I going to 0, right? So if you want to think about this a bit more mathematically, you can look in phase space. And so we don't need to know about the R's, but the current state of the system is going to be represented by a point in this lower left triangle. And if you think about it, the infection is a move up and left diagonally in this space. And so if you took time out of the picture, which is a very common analysis trick, you just look at the events and don't worry about when they happen. It's what I said about direct simulation. You're going to move up and left with probability proportional to the transmission rate at that point, and you're going to move down with a probability proportional to the recovery rate. So these trajectories here, or that's the same trajectories, but just transformed into this space. And so it's a series of moves up and left and then down, right? And these are sort of one-way moves, right? Like it's a one-way system. You go through S to I to R. So there's no backtracking, right? And what you see is the epidemics all end with they all end at I equals 0, right? Because both of these rates depend on I, proportional to I. So this whole line here of I equals 0 is a stopping point for is an absorbing, they're all absorbing states for the chain, right? So all of the x-axis is absorbing states. And yeah, first thing to note is you don't tend to get absorbed in the bottom left corner, right? So there's some susceptibility left at the end of an epidemic. And this was really one of the big early insights that these models gave, that even when things like miasma theory were knocking around, people were kind of aware, that people got diseases from animals or like bad food or something, right? And that would sometimes then spread from person to person after the initial introduction into the human population. And they saw that it kind of weakened. So they saw that you'd get a growth of infections, then a decline. And so the big alternative hypothesis to this model was, well, the pathogen somehow weakened by passage through humans. And now we know that basically the viral particles, the viruses you can sequence and look at the end of an epidemic are normally not that different, or don't need to be that different to the early observations. And so this rising and falling is mainly explained by the change in the humans, which is that the humans become immune. And that's why you see this die out. And it also interestingly means that I'll get on to the next insight later, but it's just to say these have always been sort of tools for thought about how infections work. So one thing you can't see so well here, just because of how visualized it is, lots of these epidemics stop in the top left. So you can see a big cloud, right, of black here, because I plotted them translucently. But what is actually going on is that, I mentioned this here, both infection and recovery rates need there to be some infections for those rates to be non-zero, or otherwise everything stops. So once you've stopped, you're going to stop on this line, and what people normally do is take n minus the number of susceptibles. So R infinity is the limit as t goes to infinity of RT. And that's sometimes called the attack rate, which is a bad word because it's not a rate, right? But that's what applied epidemiologists like to call it, or final size, right? So mathematicians will often call this the final size. So that's an integer random variable. And for those parameters, this won't be true for all parameters, but for those parameters, this random variable has a bimodal probability mass. So what that means is there's some epidemics are very small and some are large, right? And so this distinction, there's been a bit of ink spilled about how to make it for finite n, but you just need to simulate and you observe it, right? And this is observed in lots of real data, and we do get these near misses where there are epidemics that probably could have spread and didn't, right? But this is quite a common pattern, this sort of U shape, right, that you'll see in even quite small. So the thing I said about household inference, I'm not going to talk about household models formally, but this U-shaped histogram is quite, you do actually see it in studies of lots of small populations. You'll see some that have bigger, some where 5 people in the household get it, lots of people where 1 get it. Not very many households of size 6 will have 3 infections, right? So you get this bimodality in the final size. Okay, so that's very nice. You can simulate. There were, I mean, when people didn't have very good computers and had a bit more, maybe because of that, had a bit more time, there was an awful lot of effort made to analyze this model. If you look at Norman Bailey's book, which is, you know, one of the hundreds of things I said I could have cited and just didn't. There were a lot of effort to derive closed form solutions to this because it's sort of just about doable. But really, they weren't ones where you just pick up loads and loads and loads of terms, right? You don't get a nice clean result from doing that. So what people tend to do is look at limits as things get large or small and so on, and that tends to be a bit more instructive about getting intuitions and insight from the system, rather than looking for explicit solutions at finite n. People tend to look for limiting solutions as certain things get big or small. So this is, let's square the population size. This is 10,000. Start with 1 infected again. Otherwise, the parameters are the same. This is another benefit of dividing by n, right? That the beta is the same and it's sort of the right scaling. So what you see is these S curves for susceptibles look much smoother. And so they just go down monotonically, and there's actually a good theoretical reason these tend to look smoother than the eyes, but it's a bit technical. So the eyes still look a bit rougher, but much smoother than the 100s, the curves for 100. And so this suggests different approximations you might want to try to make. But the most common one is now the one that everyone looked up during COVID and said, oh, I think I could generalize the SIR model. Right? But there's been quite a lot of generalization of this, but it's the first thing that's normally written down. So if you let the little letters be the expectation of the random variable divided by n's, their proportions, then they're going to solve these 3 coupled nonlinear differential equations, right? So the SDT is minus beta SI. I'll talk later about how you sort of hand wave at deriving these. So dIdt is beta SI minus gamma I, and drdt is gamma I. So again, roughly speaking, corrections to these come in at the square root level. So these will be like a, so formally, so there's like a 1% error, but actually that doesn't really capture what's going on that's different between the differential equation and the random variable, because so these dashed dotted lines are the solutions to the ODEs, but scaled up, right? So scaled back up in size to the population, right? So that's treating the differential equation as an approximation to the finite system. And so these ODE limits are very powerful, very important. But what you see is that there's a lot more variability in, so each of these trajectories looks quite a lot like it, but there's kind of a shift on the y-axis, right? Oh, sorry, the x-axis, right? So it gets the shape right, but there's this early variability. So really, for this limit to hold, you don't just want n to be big, you want all of Si and R to be big. And early on, I is normally not big. So that's why these differential equation limits are not quite the full story about how we think about taking large n limits, because there's a bit early on where I is small, and even if it's going to end up spreading through 1 billion people or 10 billion people, like a global pandemic, that early randomness is going to have a big effect on actual trajectories. We saw this in COVID, we saw it in 2009 flu. Every new pandemic, you get this period where there are little bursts of cases, little outbreaks, and then it takes off. Right, that's a very, very common pattern. How many of those little bursts you get is very variable from country to country. But every country in the world was capable of spreading COVID quickly, right? It just took different amounts of time for the wider spread to start. Okay, so let's have a quick look at what those ODEs tell us, though. So the first thing to note is, like we'd sort of expect from the stochastic model, I is naught is a steady state. So we can perturb around, so this is standard, like ordinary differential equation analysis. You can perturb around the susceptible point. So we'll start with S naught as 1 minus some little epsilon, and I naught as some epsilon. And then you see that early in the epidemic, the I naught, the IT will grow exponentially with corrections of order epsilon squared. So you'll get growth if beta is bigger than gamma and shrinkage if beta is less than gamma, right? Which is nice because that's, intuitive and what we'd expect. But another interesting one is that when DID, and this is very hard to get in the stochastic model, when DIDT is 0, either I is 0, or S of t is gamma divided by beta. And so that second condition is the point in the epidemic where you expect it to turn over due to the acquisition of immunity. So I said this thing about what the model shows you is that epidemics go away because the host changes, right? We acquire immunity. And you can be quite precise here about how much immunity needs to be acquired for that turnover to happen. So this exact point, this here exact inflection point of the I is when S is gamma over beta in this model, right? And again, I'll generalize that in a little bit. Okay, so that's the ODE limit, and one of the key insights that you get from it is that this turnover happens due to susceptible depletion, and then it happens in such a way that you don't end up infecting everyone, because that happens with a finite susceptible population, and then this kind of final tail of the epidemic is never quite big enough to fully deplete the susceptible population. You always have some people left, right? And again, this is observed, right, in outbreaks. You have something really infectious like chicken pox goes through a whole school. There'll be a few kids who don't get it, right? Okay, so the other large N approximation is using a branching process. So this is a kind of Markov chain in this case, but one that we can solve. So I said to try and solve the SIR Markov chain by explicitly is very hard, right? Branching process is much more tractable. And what you do is ignore susceptible depletion. So that's kind of justified here because you say during this first unit of time here, the susceptible population is basically N for almost all the trajectories. So you can be precise about that. And then you get a random process of infection and recovery, but you don't keep track of the susceptible population. And that's a branching process. And the branching process, a real-time one, has two features of the model you need to know, right? So the first is omega. That is the rate at which you get a branching event. And then you have a probability generating function of what happens at the branching event. And so the branching event, you either get one particle becoming 2, that's the same as an infection, right? Or you get one particle becoming 0, that's a recovery. So this feels like introducing a load of other terminology, but that's just the branching process literature talks about particles and branching events, right? And rates of that. So this is just a way of translating infection and recovery into branching. So instead of saying that an individual infects, right, you say it branches and makes itself and another new infection, right, and carries on. So you have a branching rate, which is the sum of the two rates, infection and recovery, and a PGF, probability generating function, which is telling you that the probability of getting 2. Do people know what a PGF is? Again, really sorry to the energy people, but this. So PGF, probability generating function of S, is the sum of the probability of a random variable being n times s to the power n, right? So this random variable for your number of offspring at the branching event is either 2, yeah, and it's 2 with probability beta over omega. So that's just translating this thing here about your probabilities of moving through S and I space. But we're just going to always assume that S is n. And this is your probability of being a recovery. And so the mean of a branching process will grow exponentially with rate beta minus gamma, right, which is what we saw for the ODE model. So that's consistent. But importantly, the branching process will tell you things about that variability in the x-axis, which is a bit more fiddly to get out, but it will help you understand that early variability and how it propagates forward. So a bit of a self-plug, we just had a paper in SciAm Journal of Uncertainty Quantification looking at how that propagates forward to the peak time. that early variability. But a lesser known result, which I was promoting to map, is that once you've written this recipe down, you get these differential equations that are in general going to be Riccati ODEs. That means the right-hand side is a quadratic. And so pi is the probability that the epidemic is extinct at time t. And you're going to get that they in general look like d pi dt. So pi initial condition starts at 0. You get minus the rate omega times pi, and then this PGF on pi, right? So this right-hand side here, 7, is solvable, right? This equation 7 happens to have a closed form solution. I think in general they don't, right? The Riccati ODEs, but there's things known about them. And you can write this down for all sorts of models, right? Any kind of other epidemic model you like. So like I said, I think how easy these are to write down is lesser known, and they're quite relevant. It's quite interesting how things die out. So let's look at this extinction over time. So this is this phenomenon I mentioned. It's not quite related to R here, but it's these individuals in the bottom left here where you never see the trajectory, right? This little patch of darker shading. Okay. So here I'm going to look at time to extinction, then cumulative number of 100 simulations, again with all the parameters as before, so 10,000 population. So you could solve these ODEs analytically. So the total probability of becoming extinct is gamma over beta. Early on this is, or it's equal to 1 if beta is less. So something that shrinks on average will go extinct with limiting probability 1, right? That's nice. That makes sense. We'd like that to happen. And like I say, I think this is a nice way of thinking about it, because if you're just in deterministic land, you go, yes, the epidemic shrinks. And I saw people during COVID going, oh, well, if the epidemic shrinks, it will stop eventually. You'll get to 0 eventually. But that mean epidemic shrinking tells you almost nothing about the exact time it's going to hit. These Riccati equations are quite easy to solve numerically, if nothing else, and they tell you when it actually hits 0, right? Which is what you're interested in if you're locking down, going for 0 COVID or something. So what you do is you get 2 splurges of, or 2 kind of accumulations of probability mass for extinction. So the first, so you get an early one and a late one, right? And the late one is the ones that generated a big epidemic, then went extinct. And you can say things about the late one, but it's a kind of topic of active research. So I said here, working out the later part of the curve should also be possible, but people are doing it using kind of hybrid models. So that was what our SciAm journal used. We tried to kind of clag together the deterministic and random model in a principled way, and various other people are working out how to do this. This is a very sort of fashionable thing to try to do, but I would say we don't quite know yet what the best way of doing it is, so that's why I'm not going to try and draw a red line through this just yet. But this early bit, that's been known for a while, and you can draw this red line through, that's the solution of this equation. And the only reason these aren't on top of each other is I've only done 100 simulations, right? If I did 1 million simulations, you'd get really, they'd be indistinguishable. Okay, so then that's the time to go extinct. Very similar is how many people are infected. So this is the, I'd already talked about final size and attack rate. It also has this bimodal structure, but kind of a bit more extreme, right? Higher gradient. So you have about half the epidemics in this case with a very small size, half with a very large size. So in the branching process, you can also work out the distribution of small sizes. So these are so small you can't see that they're not all just 1, right? But they're not all just 1. You'll get some that go to 2, then go extinct, 3, then go extinct, and so on. And there's this nice closed form expression for those probabilities, that's in red. And again, if I did 1 million simulations, the grey bars would be like perfectly on top of the red dots. So that's also lesser known, but very doable. And then what about the big ones here? Now, this is an incredibly cool argument, in my view. If you've not heard it before, hopefully this will be a fun thing that will stay with you, because it's a very, it's reasoning rather than just having to follow the chalk, right? So suppose we have a very large population, but we're not going to commit ourselves to any particular approximation. We're just going to reason verbally. So what I'm saying here is, yeah, this final size argument we're going to make can be quite powerful and generalizes to a lot of systems. So consider an individual at the end of the epidemic, and you pick them uniformly at random. And that will have, because you pick them uniformly at random from all the n people, and you've said that there are R infinity people who were ever infected, they've got a probability that I'll call little s infinity, which is 1 minus that R infinity over n. There's just that independent probability for each person you pick uniformly at random of them being still susceptible at the end of the epidemic. Then to have remained susceptible, each of the n minus 1 other individuals in the population must either have ended the epidemic susceptible themselves, and that's going to be probability s infinity, or they did become infected at some point, which has probability 1 minus s infinity, but they didn't transmit to the individual considered. They didn't happen to that pair of people didn't happen to have a transmission event between them. And that's probability, what I showed you there, it's gamma over gamma plus beta, except the beta's got to be rescaled because we're just thinking about 2 individuals, not the whole population. Okay. And so putting those together gives you this, oh, I've missed out the gamma over gamma plus beta. I reread these loads actually, but okay, so copy that gamma over gamma plus beta into that bracket bit there, right? So because you've got 2 things that are disjoint bits of the probability space, so you can sum up the s infinity and 1 minus s infinity, but then this one needs to be multiplied by that probability that you don't, you didn't transmit. So you did get infected but didn't transmit for all of the other n minus 1 people. So you take the whole thing to the power n minus 1 because that has to be true for everyone. They either weren't infected or they were infected and didn't infect you. And that has to give you the probability s infinity, right? So this 10 is a consistency relation. And if you take the large n limit of that, you get this expression here. S infinity is x beta s infinity minus 1 over gamma. And so there is the red line, right? That you get by solving that implicit equation numerically, right? And you can get a central limit as well if you want, right? So you can get that limit. The central limit doesn't have a nice verbal thing. It's quite, but people can derive it. Okay, so those are all insights that you get from thinking carefully in the large n limit about the SIR model. But by showing you for 100 people, you see that they kind of carry over to almost all size epidemics, that they'll tend to grow and shrink, start shrinking when you've hit herd immunity. There'll be, some that are small, some that are big. Right, so the insights you get by analysis at large n pretty much carry over to all SIR type epidemics. So I've taken my time. It's finally time to consider R0. So this can be defined verbally as the expected number of secondary infections per primary infection early in the epidemic. That isn't a formal definition, but you want any formal definition you make to agree with that verbally. Right. So for the SIR model we've been considering here, in the large n limit, each individual, you're making new infections at rate beta early in the epidemic for mean time periods 1 over gamma. And so the expression beta over gamma will agree with that verbal definition of R0. It's how many people you infect on average if you're an early infective in the epidemic. Okay. And so then let's go back to all those things that we just derived and rewrite them in terms of R0 instead of beta and gamma. So if R0 is less than 1, an epidemic started around the fully susceptible fixed point will shrink. Second typo. If it's bigger than 1, right, there should be a bigger than. The probability that the epidemic started from 1 infectious individual dies out is 1 over R0. Right? Otherwise, it gets big. If it does not die out, in this case with the R0 bigger than 1, it'll grow exponentially with rate proportional to R0 minus 1. Epidemic prevalence will peak when the susceptible fraction is 1 over R0. And then the final size, R infinity, will be given in terms of R naught by this equation 12, right? So not all of these generalize, like if you go beyond Markov, it isn't always a 1 over R naught probability, I think. But it depends how you have to be a bit careful about all these generalizing, right? But you can, all of these make good sense logically. When you think about what R naught is, right? And so a lot can be got with just verbal reasoning, not going through the equations like I did. Any quick questions on the, not quick, any questions on the SIR model? So I'm just about to do that. So that's great. Perfect kind of question. Shows that but yeah. So I'll show a kind of toy example, but not a million miles from how people really use it. That's a huge thing. Yeah. Can everyone hear me all right? Actually, I sound really loud in the microphone. Am I loud? I can talk. Yeah. It's variable. So Ebola outbreaks, we really hope to get a true zero for Ebola. In between the outbreaks, I really genuinely believe there are 0 human infections with Ebola. The reason they don't fully die out is you can get people losing immunity. That's the big one for COVID. Your immunity doesn't last very long. So either it's because for COVID, it's a combination of you lose immunity and the virus mutates to escape your immune system. For things like measles, you have lifelong immunity, but people keep being born and are born susceptible. So that was what caused measles and things to persist. But lots of things do die out. You don't hear of them, and some. So even measles in Iceland fully died out in between introductions, right? So small isolated populations, measles would go through, and people weren't being born quickly enough to cause it to persist. So there's this idea that measles needs a big enough population or critical community size to persist at non-zero levels. So you do see zeros. You see zeros for things where R naught's bigger than naught. You see zeros where R naught's sometimes bigger than naught, like Ebola. Then obviously for hantavirus, that was a very small limited outbreak. So that was one of the R naught less than. So hantavirus is like this bit here, right? You're just getting small chains of transmission. It was never going to go global. Ebola is the scary one because it seems like R naught can be bigger than 1 over quite sustained period. You know, the R number can be bigger than 1 over quite sustained periods of time. Whereas hantavirus is like hopeless. It's really, really bad at spreading person to person. It's only because cruise ships are so. I'm about to talk about cruise ships actually, but cruise ships are just dreadful for disease transmission. And the fact that hantavirus only spread to a few people in that incredibly cramped environment, which is the most favourable thing for disease transmission, tells you that hantavirus is like R naught well below 1. So yeah, you do see all of this stuff. I think almost all this, like I say, people keep going, it's a theory, but for everything I've said, we could all show you lots of data sets where it's sort of, the models are very crude quantitatively. Well, the SIR model is quantitatively not a great model of lots of these, but qualitatively they do capture all the things we see. And then lots of the statistical work is trying to get a good quantitative fit. Right? So yeah, any other questions? Energy people, you may be doing epi people a favour if I've said something where the epi people are thinking, oh, I don't or just general behaviour people. Okay, so here's a real example, and it's a slightly toy example, but not atypical how these get used. So this is the way that applied or shoe leather epidemiologists tend to report their data. So you know it's an applied person because they plot it as a bar chart, right? And this is called the epi curve, and that normally always means a bar chart. So my first advice to mathematical students who want to work with applied people is bar charts, right? They like seeing bar charts. And it's because actually, in fairness, they then release the whole data set, right? Because it's integer. So they didn't release this as a CSV, but I just typed the numbers in, right? Because so you can, it's actually quite helpful for secondary use of this published data that they do a bar chart. And so this is the epi curve for norovirus on a cruise ship. And the literature is absolutely full of these. So very sorry if you do like cruises, but the outbreaks are always just really big because people are very close. And so the SIR model can be related to data. So because this is quite small, it wouldn't be ideal. I'm saying start with 3, these differential equations. So I'm going to fit the differential equations to this data. I think most epi people here would go, well, if I was doing this for real, I'd fit a stochastic model. It's a small population. So that's why I say it's a slightly toy example. So the epi curve, one important thing is that doesn't show prevalence. So I of t is prevalence, how many people would currently be infected if you went and swabbed them. But what they show here is this is cases. So it's the new infections they've detected on that day. So that's incidence, right? So what you actually want to do is not do like a least, so a very common like error is to do least squares between the I curve in your SIR model and the epi curve. That isn't quite right. What you should really do is work out the cumulative incidence. So how many new infections is your model predicting over the day? So that will be the integral of the beta SI term, right, between a period tau and t. The expected number of new cases is the integral over beta SI. And so you can work out this integral by just adding a differential equation to your system 3. So d cumulative incidence dt is beta SI, and that doesn't go down, right? That's your expected number of cumulative cases. So then suppose that this here is new cases is y, and that's observed at times t1 up to tm. Since they're integer, I'll use a Poisson link function. Again, this isn't quite right because what's it Poisson of and so on, but it's a way of linking this ODE to data. So I'll let the mean be the cumulative number of cases in my ODE, and I'll assume for convenience that T0 is 0, right? So that gives us a model with 4 parameters, the beta and gamma, and then the initial conditions of the ODE. And then in terms of those, I can write a likelihood function. So I'll assume that the likelihood of those, hang on, I'm too Bayesian, these should be the other way around. Okay, third typo. So this should be likelihood of the observed y given theta and t. So it's the observed cases given the parameters. I've got this, yeah, same typo here, right? So just switch the y and the theta because this is data given parameters. So it's going to be a product of Poissons of that integer given the expected cumulative cases. And so then you can just do numerical maximum likelihood estimation and do uncertainty quantification by working out the Hessian. So this is quite standard asymptotic classical statistics. So you can show that asymptotically everything's normal on the MLE with the second derivatives of the log likelihood giving you the covariance of that normal, right? Okay, so if I do that numerical optimization, it's all kind of wrong, not what a cutting edge person would do. But as a sort of example of how these are used, you get an R0 of about 2.1. That's pretty reasonable. That's a, you know, each norovirus case, each norovirus infection infecting another one. TI of less than a day. Now, you're ill for longer with norovirus, but the important point is how much of that period are you infecting people for? So in this circumstance, people were probably isolated very quickly. They start vomiting. So saying that you're in a position where you can really infect someone before you get contained to your cabin is probably less than a day, right? But you're right, the period you're ill, so the period you're infectious for is different from the period you're ill for. Yeah, if you isolate. So this TI is about how long you're infecting people for. Then being removed, you could still be vomiting and, you know, poorly tummy, but you'd be in that R class because you're not playing a role in the ongoing epidemic. You've been removed from the system and put in a cabin and getting meals outside the door that you take in or whatever, right? And then it also optimizes at like one initial infection. And now, this is also about how you interpret the parameters. That there were over 1,000 passengers, but I'm letting it estimate the early susceptible population because some people will be immune. They will have had norovirus recently enough that they have antibodies and are immune. We don't know how many that would be on a typical ship. Also, some might just, the ship itself might be spatially segregated. So there might be a lot of those 1,000 people might just not have been in the areas where spread was going on. So you don't really know that the susceptible population is the whole ship. So again, it's not unreasonable that only a quarter of the ship would have been either biologically not immune or in enough spatial proximity to get infected. So these are not unreasonable parameters, right? And so eyeballing it, you know, yeah, that's all right. It goes up and down like the curve, but you should never really show a figure like this because you should show uncertainty and everything. So if I do a parametric bootstrap, which is I get that maximum likelihood for the parameters, work out the Hessian, and then pick from the normal. I do that 100 times, I get these 100 curves. So that's my uncertainty under parameter uncertainty. The model itself has got no aleatoric or demographic randomness. It's a deterministic model, but I have uncertainty due to parameter uncertainty in terms of what a future epidemic on an identical cruise ship would look like. And then if I combine that with Poisson intervals on the cases, you can see actually that's a reasonable fit, right? Again, I keep on saying this is a posterior check, but it's not, right? That's part of Bayesian workflow, but a classical or frequentist statistician can look at this and go, yes, that's reasonable under uncertainty. So why would you do this? Why would you care? So sometimes you'll do this early in an epidemic and extrapolate the exponential. There was lots of that during COVID. But here you might ask a question like, suppose we had a norovirus vaccine, which we don't get, they aren't very effective. But suppose we did, and suppose cruise companies said to people, we'd like you all to vaccinate before you come on our cruise with norovirus. So what I can do is I can vaccinate half the people who were initially susceptible. So I can take 125 of these and put them in the removed class at the start. And the point is, because the model is mechanistic, that lets me answer counterfactual questions. So statisticians will often go, why did you go through all this pain of fitting an ODE model when that curve looks a bit like a gamma distribution or something, you know? And that's a reasonable question, but the gamma, if you fitted, say, a gamma or log normal or something to the times of cases, you wouldn't be able to do this counterfactual analysis. So here I say, suppose I vaccinate and the vaccine has a 50% success rate of making people immune, then the outbreaks would look like these blue curves. And so exactly the way they're used in real life would be someone would do something like this, probably a bit more sophisticated. Then you'd look at the cost of a vaccine, the health economic cost of someone getting ill with norovirus, and you'd look at the difference between the red and blue curves and say, does that difference in terms of the reduced disease costs justify the cost of vaccinating people or vaccine development, right, if people haven't developed the vaccine. So that's how the models are used day by day, right? They inform, you know, most recently there was a decision that the government's going to offer meningitis B vaccines, right? So the Joint Committee of Vaccines and Immunisation would have run an analysis much like this, where they fitted models to meningitis and tried to work out, is it worth offering more meningitis vaccination after these outbreaks we had in Kent and so on. But it's normally not as clean cut as this, right? The data is normally messier, lots of sources of data. But that's an example of how they use day-to-day. COVID was a bit unusual in that COVID, there was lots of extrapolating exponential curves. I don't think that's the main use of epidemic models. It's mainly to capture the fact that because you have these feedback effects here, reducing the susceptibility by 50% doesn't reduce the attack rate by 50%. So you need to do that calculation carefully. And that's what the model's letting you do here. Okay, so about an hour, there's probably a natural time to stop, take the break, have coffee. Any questions on what I've said? So has any epi person learned something? Not been completely teaching your grandmother to suck eggs type thing? No.